Now we'll have an EBM. Anybody know what blazes an ROC curve is?
Receiver operator curve.
Very good. It's a receiver operating characteristic curve. Answers the question, right? My work here is done. So you see this, you're like, fine, that tells me nothing. So what exactly is a receiver operating characteristic curve? As it turns out, it's kind of cool. Receiver operating characteristic curves, developed during World War II, it actually ties into signal detection theory. And what it did is it looked at, it was described how accurately radar distinguished enemies from people that you don't shoot from just garbage like monkeys running around in the field. So this is where it came from. But we actually take this now to statistics to say, if we're looking at a test, how well can this test discriminate between abnormal, normal, and garbage? So that's where it comes from. But unfortunately, ROC curves involve spin. And for those of you who can't see in the back, this is the original horror movie, right? Yeah. Number 2 after Psycho. There's Linda Blair, who grew up to be a very pretty woman, by the way. And Snout, which I totally adore. If you've not heard me write incessantly about spin and snout in the past, I can't stand the concepts. It confuses me to no end. I think it's much easier in my brain to remember that sensitivity and specificity, how exactly it works. Screening test, you want a screening test that is sensitive, specific. Very sensitive. What happens if you have a very sensitive screening test? What do you miss? Lots of false positives, lots of false negatives. What do you want? You get false positives. So basically you want to pick out a sensitive test. You want a very sensitive screening test because you do not want to miss any of the true positives, but you're going to do that at the expense of picking up some false positives. That's okay. You don't want to miss anybody. Specific test, on the other hand, explain. Better is a diagnostic test because a sensitive test, a specific test will help you what? Rule out disease. So if you get a negative test and it's a very specific test, a negative test says, okay, you truly do not have disease. Much better for a diagnostic test. I have no idea what spin and snout are about, so don't even ask. But more specifically, sensitivity and specificity actually depend not only on the quality of the test, but also the definition of where you put the cut point of what's normal and what's abnormal. So you've got something that you say, okay, where do we define hypothyroidism? What's an abnormal TSH? There are a lot of people who walk around with a TSH of 6, and they may be completely normal. But we've defined the cut point as 5.5 roughly. And that's where TSH becomes abnormal. However, there are still some people who are going to be normals that you're going to pick up when you make the cut point there. So where you set that cut point has some determination on sensitivity and specificity, and also it factors into how the test works. Most tests don't distinguish normal from abnormal with 100% accuracy, correct? There's not a lot of tests with that. The last normal person, your cutoff is right there, and it absolutely distinguishes normal from abnormal 100% of the time. So again, we have a trade-off between sensitivity and specificity. If you put your cutoff real high and you say, you know what, I don't want to miss anybody, I'm going to put my cutoff way over here, very, very sensitive test, but you're going to have a lot of false positives. Likewise, if you put your cutoff way over here, you say, I don't want to tell anyone that they have a disease when they truly don't, you're going to end up with a bunch of false negatives there. You're going to say, no, everything's okay, but truly it may not be. So, oops, this way. Here's it kind of in graphical form. If you can see that the big blue line here is true negatives, people without disease. Here are people true positives, those with disease. Again, normally you see a little bit of overlap. Not everybody, at this point right here, if the two curves came together and at this very point down here you could make your cutoff, great, it'd be a 100% perfect test. But there's some overlap. And so again, wherever you decide to make your cut point helps determine how many true negatives you pick up and subsequently how many false negatives you get and how many true positives, false positives you get. So what the ROC curve does is it basically plots true positive rate versus false positive rate. So it's true positive rate, which is sensitivity, versus actually the inverse, or 1 minus specificity, which is the false positive rate. Here are a couple important things about the curves. When you're thinking, reading an article that says the ROC curve, gave it this area under the curve. What the heck does that mean? Okay. Closer the curve is approaching the top and the left-hand borders, the more accurate the test is. So if they show you a picture of the curve, if you get a curve that's basically approximating the 45-degree diagonal here, in essence it says sensitivity and specificity are about 50%, meaning that you may as well flip a coin. But if the curve is pushing closer and closer and closer up to this upper left-hand corner, the point there is that the test gets more and more accurate. If you really want to be fancy, and you understand likelihood ratios, which how many people understand likelihood ratios? Totally baffling concept. But if you actually do the slope of the tangent of this line at various cutoffs, that's going to give you a likelihood ratio. Fascinating. But the area under the curve is a measure of the test accuracy. If you get 1, which says the area under the curve, if this curve came right up here, hit this corner, came right across the top, the area under that curve would basically be 1, it'd be the whole volume here. So that is a 100% perfect test. It's going to give you 100% of the time, it's going to discriminate between normal and abnormal. If you get an area under the curve of 0.5, that basically is this line right here. And again, it means that if you have a normal and an abnormal subject, you throw this test at them, what is the likelihood, or how many percent of the time is this going to discriminate normal from abnormal accurately? If it's 50%, you may as well flip a coin. You've got a 50-50 chance of the test getting it right. It's a worthless test. If you think about this kind of on a grading scale, at least the old grading scale, not the new grading scale, between 0.9 and 1 is considered an excellent test. And as you notch it down, as the area under the curve decreases, this curve kind of gradually approximates, this 45-degree line gradually approximates 0.5, the test becomes less and less accurate, meaning that it's got less and less likelihood of accurately discriminating between normal and abnormal. And the area under the curve basically measures discrimination, which says the ability of the test to correctly classify those with and without disease. Is that completely baffling? Okay. So the key thing here is if you read this, and I had to go look up to see how this works, so I'm not the magician here, but the couple numbers that will come back is the area under the ROC curve. Remember, high numbers approximating 1 is better. Closer it gets to 0.5, the more worthless the test is at discriminating normal from abnormal. And so with that, here's what my brain feels like. I couldn't resist more Linda Blair. It's just such a classic film. And it just was kind of, it's number 2 in terms of horror movies, Psycho being number 1. So, any questions?